Hello everyone, my name is Dmitry Vostokov. More than 2 years has been passed since I presented the second version of complete cache and ham memory dump analysis webinar, and more than 3 years since its first version. Before that time, I found this topic a bit neglected, so I had decided to summarize it and make a presentation. Many new memory dump analysis patterns have been identified since that time, and new training courses became available, so I decided to make a new revision. This is a big topic, and I assume you already know what kernel process, physical and virtual spaces are, how to set up and use symbol files, basic WinDbg commands to get stack traces and list loaded modules and their information. First, I remind you and discuss the very basic concepts like what is a physical memory space and how it relates to what we see in WinDbg debugger when we open a complete memory dump. Then I discuss a pattern language to communicate memory dump analysis findings. Next, I do a quick hands-on demonstration and finally provide a short incomplete guide. You can type your questions and I do my best to answer them either at the end of the webinar or publish them later on a special page for this revision. Here in this section, I talk about the need for complete or physical memory dumps and how to force them. I talk about the differences between various memory spaces, major challenges we face when we start looking at memory dumps or physical memory space, and I also talk about common WinDbg commands, absolutely essential to know. In this presentation, we cover only Windows desktop and server platforms, but the pattern-oriented approach can be reused for other platforms and products as well. Physical memory analysis can be live, for example, during a debugging session, or it can be a post-mortem via memory dumps. The same catalog of memory analysis patterns is used. For example, a memory leak can be diagnosed on a live system by examining memory at different times, and in the case of post-mortem memory dump analysis, we need a set of consecutive memory dumps saved after some interval. However, in the case of a live analysis, some patterns may not be available, such as related to memory dump specifics. Why do we need complete memory dumps? Suppose we have an incident when a system doesn't respond to user, program, or network requests, appears hung or very sluggish for users. We experience long delays. In such case, we can get a kernel memory dump to check for various patterns such as spikes in kernel mode, kernel pool leaks, insufficient physical memory, extensive paging, resource contention, or deadlocks between executive resources, famous logs command. However, we might not find all of that and would need to look at processes to find if there are any blocked GUI threads wait chains between processes, deadlocks in user mode synchronization mechanisms such as critical sections, process heap corruption, CPU spikes in user mode, error message boxes, and so on. In summary, we would need to look at process spaces that are missing in kernel memory dumps. Other typical scenarios occur in terminal services environments like user session freeze or connection denied messages. Sometimes it is the only option available when we want to examine a live system offline. There are many methods to force a physical memory dump from a live system. Some methods freeze all CPUs except the one that is currently saving memory directly to a page file, bypassing file systems. This ensures memory dump consistency. Live methods, therefore, may save a non-consistent memory dumps as parts to be saved may change pointers to the first parts already saved. However, the latest versions of Windows sysinternal's LiveKD tool provide options for more consistency. And you can also find various third-party tools for memory acquisition as well. Before we look at debugger's view of physical memory, we recall a few definitions. For example, physical memory space is just a linear ordering of physical memory cells and some other units. A virtual process memory is how a process sees its memory during execution and how we see it in a debugger. Process pages can be randomly distributed in physical memory, and even some can be located in a page file. However, when we break into a debugger on a live system or open a complete memory dump, we see a linear ordering of memory cells that comprise the current process memory. The debugger takes care of this physical to virtual address space mapping. Notice there can be also gaps in virtual memory as well. So when we open a complete physical memory dump, we see the virtual space of the current process, called the current process context. We need to be aware of the current process, and when we switch to another process, we need to make sure that the debugger switched to the appropriate physical to virtual space mapping and reloaded symbols for user space modules. Kernel space always stays the same. The simple approach for blue screen crash dumps to check their problem thread stack traces is no longer applicable here. Even checking a few processes of interest is not enough because we might miss something. All challenges here are obvious except the third one about examining threads. Because threads belong to processes, when we examining them, we need to make sure we also have correct process context, physical to virtual memory mapping, therefore, and also correct symbols for user space. So we need to make sure that symbols are reloaded. In case of huge physical memory, there exists another alternative. The so-called Fibre Bundle is a memory space that consists of kernel space and individual process virtual address spaces. Whereas a complete dump of physical memory might miss some pages residing in a page file, a fiber bundle set of memory dumps is more complete in this sense because missing pages of process memory are brought from the page file when we dump individual processes. What we lose here is synchronicity that could make some memory references inconsistent because kernel and process memory dumps are generated at different times. So now we come to common commands in WinDbg. So first of all, because the output of commands is very lengthy, most of the time it is useful to open a log file and later analyze its content as a text. To save time, we can include many commands in a script. Such scripts are also useful for secure environments if you don't want to send a memory dump but prefer to extract textual information and send it to third-party technical support. So you see there are two broad categories: view commands and switch commands. Let me see, there is a possible question. Okay, there is a question about can the dumped memory take a bigger space than RAM memory because of zero structures? I would say it depends. If you dump a physical memory, then the dump should be like the exact size of physical memory. Later, Windows 8.1, for example, allows you to preserve a page file as well for offline analysis. However, if you dump, I would say, a fiber bundle, then of course it could be possible that the total sum of memory is greater than RAM physical memory because of page file contents brought in when we dump individual processes. So did I answer your question? So okay, let's continue then. So we see there are view commands that dump everything on selected process and threads, and switch commands. So first we cover view commands. So this is a list of commands. It is corrected for the latest WinDbg from Windows SDK 8.1 and 8.0. I mean the flags corrected, but commands stay the same. And we also use these few commands during exercise. I later post this presentation on website, so you will be able to use it as a reference. And so switch commands. So for example, after using view commands, for example, if we use the first command that lists all processes and we all have this saved in a log file, and then for example we want to examine particular process or thread, then we need to use switch commands, and we should not forget to use flags that direct WinDbg to change process context automatically and reload symbol files. So now I briefly talk about patterns before we do exercise. So a few words about pattern-driven analysis. Here I provide you a typical pattern example. For example, we identified process heap corruption and suggested program instrumentation to narrow down a set of suspicious modules by using either gflags from debugging tools for Windows or application verifier. And most recently, I consider pattern as like a set of recurrent identifiable indicators or signs. It's like a problem. There's a problem. A set of some indicators you see in analysis artifacts such as memory dumps or traces. On this slide you see also a few pattern classes like broad categories or blocks. An example of a blocked thread could be a print spooler that attempted a print driver setup, presenting a dialog box with some service loaded module showing an error message box, not visible because of system session, not console or user session attached to a desktop. Wait chains can include threads waiting for critical sections, executive resources or involving inter-process communication mechanisms such as remote and local procedure calls, so-called IPC, LPC or ALPC mechanisms. Resource consumption can include kernel pool memory, CPU and handle usage. Corruption signs can include heap and pool corruption, freeing the same memory twice, and special processes can include Windows reporting executables such as verfault, so on to Dr. Watson for all the versions. So there is extensive pattern classification on Software Diagnostics Institute on dumpanalysis.org. And users of Software Diagnostics Library can have access to advanced pattern classification and pattern catalog, and also all owners of memory dump analysis anthology volumes. Now I show you a few fragments from the log file you can later download after you get these presentation slides. So for example, a blocked thread, you see a message box highlighted here, the function call. I also show you, this is from exercise, the output I'll show you later on. Then we have an example of a wait chain. We see that a thread is blocked on a mutant, mutex, which is owned by another thread. So next example is handle leak, handle consumption. You see that the process application E actually has more than 20,000 handles. And another example is heap corruption in user space that triggered exception processing, and you see also this thread is waiting for a process object. That probably Windows reporting. We try to check that during exercise. And another example, special process. You see in the output of processes, we see Windows error reporting process started at some time. So this might point to exceptions. And before exercise, we also outline common mistakes. The first mistake is when we forget to apply switches or flags to WinDbg process and thread view and switch commands. The second mistake is when we forget that some commands show only partial stack traces based on the default number of stack frames to display, but I think this is now solved in the latest versions of WinDbg. But nevertheless, we should remember that we might not see the full stack trace. The third mistake is when we look only at a subset of processes. Other mistakes are obvious except the last one, not doing explicit symbol qualification. So here sometimes we need to explicitly qualify symbols when we have both 32-bit and 64-bit modules loaded at the same time, such as NTDLL, because now we have almost all computers are 64-bit, but lots of programs are still 32-bit. Also, as we would see during exercise, most of the time we would need to list both 32-bit and 64-bit stack traces, and for this we need a script that can be found on windbg.org. This is the site I created just for quick links. I update it from time to time, so basically quick links for debugging, tools for Windows, symbols for Microsoft and Citrix, some extensions, books, and scripts. For example, this complete stack trace. So I strive to update it from time to time, so some updates come in next year. And so we come to exercise agenda. The approach I devised for this presentation is to run a few specifically constructed applications that model abnormal software behavior. So the first two steps I did before the presentation, actually more than 2 years ago. And I also pre-analyzed the memory dump by running a few commands and saving the output in a log file, especially dumping old processes and threads. It takes some time. And these log files I will make available for download after this presentation. So there are a few processes you can download. They're named as application A, B, C, D, E. And I also run two versions of application A, 64-bit and 32-bit. So if you want to reproduce this analysis on your own system, you can download this from Pattern Diagnostics website and run them in alphabetical order and then wait for some time. So application A is devised to highlight block thread and message box patterns. Application B and application C are about weight chains. Application D is about dynamic memory corruption, process heap, and special process patterns. And application E is about insufficient memory, handle leak, and spiking thread patterns. So in the first version of this presentation, you can still actually see slides 3 years ago. I used the Not My Fault tool. For the second version, I decided to use a simple approach by killing session 0, CSRSS process in Task Manager. And also, the first version used 64-bit Windows Server 2008 release 2, and the second version used 64-bit Windows 7. And for this, the third version of presentation, I reuse the same dump file from the second presentation from 64-bit Windows 7. Actually, I think you no longer can kill CSRSS in Windows 8.1. I think you can do it in Windows 8.0, but not in 8.1, but you can use other third-party tools to kill, and this still works. So now I switch to a WinDbg session. So I already opened a dump. You see this is the newest version of WinDbg. So I open my dump. So we get lots of output. First of all, what we do, we apply symbols. No, first of all, we open a log file first. Let's open a log file. So let's save it. I post this session log file later on. So I open the log file. So then we fix symbols. And then do reload. Actually, you see that time passed and the TDLL is no longer available from Microsoft Symbol Server, but because it has lots of exported symbols, so this is still applicable, and it will not change our analysis. So what is the current process? We use bun process. It is process with many threads, and this is task manager. So this is the current process context, and the virtual space we see is for this process. For example, we can see user space modules for this task manager, and LMK kernel space modules, so drivers basically. So when we switch to another process, these kernel space modules remain the same, but of course the user space map will be changed. So here, this is for task manager. So the command to list all processes and their thread stack traces 3F03F. This is a time-consuming command, and I already did this command before. Actually 1F I did. 1F removes process environment variables for security reasons, and this is a lone output, as you can see. So I already created this, so it lists all processes and threads. So but what we do here, we only list the short information. So we use bun process 00. So basically just get the list of processes. And what we see here, we notice that process that belongs to application E has 20,000 handles, so definitely we have a handle leak. When we dumped the whole output into log file, we can search for some textual patterns. For example, let's go to the beginning. So what here, for example, we can search for message box, and we find one thread that belongs to application A that actually shows a message box. So this thread belongs to process which has this address. So we, for example, if we are interested in this process, we copy this address and then use now .process command, switch command, use flags to specify this process address, and now the current process is application A. For example, we can see it if we dump modules. We see that this is different process space that belongs to application A. And if we are interested in a particular thread, so we can make this thread current. So we copy this address, do .thread, and we don't need to apply flags if we are in the same process context, but it's better to do it to do /r/p. Then we have this current thread, and if we type kv command, we get this verbose stack trace that shows a message box again. What other patterns we can search in the textual output? You go back, go to the beginning, and for example we can search for mutants, and this is so one we skip because owning thread is 0, and the next one we see thread that belongs to application C is waiting on a mutant that is owned by a different thread. So let's switch to this thread. And if we do kv, actually we don't switch, we actually list this thread using list command. So for example 1f, so here what we see that thread that application C thread is waiting for belongs actually to application B, to a different process. So what we here identified a wait chain between two processes. And what we also search for, we go to the beginning and search for something like critical, maybe critical section something, and or crit. Actually we need to go to the beginning, so let's search for critical. Let's see, there's nothing, so let's go back. Yes, what I think that there's a problem with application C, because we can't download symbols for NTDLL. Let's try again. No, it's not possible to see. So what I then do, I open a log file from the previous presentation that I did 2 years ago when NTDLL module was available. I think so. This was the log file, and because NTDLL and some other modules were available, symbols for NTDLL were available, we were able to actually find critical section in the output in the log file. And so what we were able to do, we were able to switch to this process and to analyze critical section weight chain. So what else we can do now? We can check running threads. I think if you repeat this exercise on your own system, and I think you will be able to get right symbols for NTDLL and analyze application C. Basically, you switch to that process and then use CS command. And analyze weight chain. You can actually get the log file from that session. So here, after we switch to process C and make this process C current, we were able to run CS command. I think there's lots of output redundant in the log file. But at the end we are able to see critical sections and see their owners. And then examine these particular threads, switch into the threads using kv command, and even do some backwards disassembly to find out their interdependencies. Anyway, so you can actually see that in the previous version, but here I can't show you because NTDLL symbols unfortunately were not available, and stack trace becomes truncated, as you see. For application C, we have a truncated stack trace because symbols not available. So maybe if you do raw stack analysis, you will be able to find out and reconstruct stack trace. And so I try myself, and if I am able to do that, I post results on the website. So now we come back to the list of running threads, and here we see that at least we see some CPUs have running threads. So first of all we check this one thread. So this thread belongs to application E, and you see that it is currently running in user space and accumulated significant amount of user time, 1 minute 25 seconds. I didn't run these applications for a long time. Actually, just to show you, for example, if we do it without flags, we get some garbage. You see there's no function names for call site. This is because we forgot to specify flag 1F to switch to application E process context, but with appropriate flags we get stack trace, and if we specify 1.6 we even get some raw parameters taken from raw stack, and at least we see symbol mapping, correct symbol mapping. So, and finally I want to show you 32-bit. So basically the log file is the output of process 03F or 1F command, but it only has 64-bit stack traces. For example, application A, there are two copies of application A. One is 64-bit and the other one, which we see here, has lots of wow 64 modules. This is 32-bit application running on 64-bit system. And if you look at these stack traces, you won't find major patterns because you need to dump 32-bit stack traces. And if we use this script, then I already did that, and we have a different log file that I put on this, I put on website. So here for each thread we get 64-bit stack trace and, if possible, 32-bit. So this is not available for system threads, but for application A. Application A, for example, we so we are looking now for, so this is application A 64-bit. Remember that we found out that it was shown in a message box, but there is also application A. We keep searching for its threads. We find out the second copy of application A that has 64-bit stack traces, but this script also shows 32-bit counterpart automatically. And if we search for message box, we find out indeed the hidden 32-bit stack trace that also called message box function. So this is all for this quick exercise. And now we continue with the rest. Just a few slides left. So now I showed you a few pattern names and their description links. Since the second version of this presentation, the pattern descriptions and case studies are only available for users of Software Diagnostics Library, or if you have memory dump analysis anthology volumes. So here are some pattern examples, but there are more than 250 patterns identified for memory analysis. And there are actually, I think there are even more than 17 pattern interaction case studies. So each case study includes several patterns, and it's useful to see how patterns are diagnosed in context or are interrelated. And this content is also available for users of Software Diagnostics Library and from memory dump analysis anthology volumes. So there is the first issue of Debugged magazine, has a very useful table and map compiled from pattern examples that shows what WinDbg commands can be used for memory dump inspection if you suspect a certain pattern. Unfortunately, more than 100 patterns have been added since the publication of this map, so it needs a revision in 2014, so this is what I do next year. Here are some useful resources, like WinDbg.org also contains links to various WinDbg related books written by me and other authors. Debugging TV is a very useful site, lots of information about troubleshooting symbols, live debugging, and I hope to do volume 7, finish volume 7 in January, so it has been delayed for quite some time. There are 2 new courses added since the second version of this training, and the old ones now having new editions. So these are training resources that mention complete or live physical memory dump analysis. They're actually 64-bit. Some of them cover only 64-bit and some mix of 32-bit and 64-bit memory dumps. And so this is all. If you have any questions, please ask. Otherwise, see you all next year. Happy New Year. All the best. And actually, starting next year, you no longer need to register with GoToWebinar because we will not use Citrix Online starting from January. And what I'm doing now, I am now moving all webinars to YouTube. So please stay in touch on Facebook or visit Pattern Diagnostics pages and website. So thank you very much for attending. Happy New Year again, and see you all in the new year. So there is a question: what is a very good sequence of learning dump analysis using books? So let me show you. There is a map, or let me double check this. So there is a training roadmap. So first of all, accelerated Windows memory dump analysis. You can start this as a very extensive and intensive course, and from that you can move to other courses such as malware analysis, accelerated .NET, or advanced memory dump analysis, and then accelerated disassembly, all that. And there is also parallel Windows debugging course, but this Windows debugging course can be done in parallel or independent from a Windows memory dump analysis course. So let me copy this. So this is roadmap. I think so. Let me copy this link. So if you're interested, so this is all. So do you have any other questions? And I also plan, there's also accelerated Windows software trace analysis if you are interested. And I also plan accelerated network trace analysis. So I planned this a year, but unfortunately I couldn't do it. So this is the task for next year, network trace analysis training. So, okay. Thank you very much for attending, and see you all next year. Happy New Year. Thank you. Bye-bye.